Hello guys, in this lesson we want to talk about the energy principles, right? So let us first define energy. Energy is defined as the ability to do work. So it is the ability to do work, that's energy, right? So we have a number of energy principles that we are required actually to know and then make use of when answering questions, specifically under work, energy, and power. Right? So the first principle that we want to discuss is the principle of conservation of mechanical energy. The principle of conservation of mechanical energy. Let us first try to highlight a few of the types or forms of energy that we are required to know. Right, number one, we have kinetic energy. Kinetic energy is defined as the energy that an object possesses by virtue of it being in motion. So if an object is in motion, it possesses kinetic energy. Okay, so it is given by kinetic energy is equal to half mv squared, where m is the mass of the object in kgs, and v is the velocity of the object in meters per second. Do take note again that velocity is a vector. It has a direction that it actually takes, right? So it's important again to remember that. So we are saying that's the formula for calculating kinetic energy. Apart from kinetic energy, we also do have gravitational potential energy. Gravitational potential energy, right? We are required to know it as well. By definition, gravitational potential energy, it is the energy that an object possesses by virtue of it by virtue of its position above the Earth's surface. So the energy that any object possesses due to its position above the Earth's surface, it is what we call gravitational potential energy. So it is given by the formula EP is equals to mgh, where m is the mass, indeed, in kgs, and g is the gravitational acceleration. So gravitational acceleration, it's a value that ranges around 9.8, rounding off to the nearest to one decimal place. So it's around 9.8 meters per square second. That's the gravitational acceleration. Then h is the perpendicular height. It is the perpendicular height, which means it is representing the height of an object above the Earth's surface, right? That's h, and it is measured in meters. So that's the height in meters. Okay, so these are the values we have. Okay, of course, gravitational potential energy. Energy is measured in joules. So is also the kinetic energy is measured also in what? In joules. Then apart from these, we also have the mechanical energy. Mechanical energy, by definition, it is the sum of gravitational potential energy and kinetic energy. That's mechanical energy by definition. So mechanical energy, it is the sum of the gravitational potential energy and kinetic energy. So it takes us to our first energy principle that we want to discuss. The first energy principle is the principle of conservation of mechanical energy. Of mechanical energy. That's the first principle that we want to discuss. Principle of conservation of mechanical energy. So it simply states that in an isolated system, the total mechanical energy is conserved. Total mechanical energy is conserved. That's what it simply says. So at this statement, let us first talk about the isolated system. An isolated system. Okay, an isolated system is simply a system in which there are no external forces acting, or non-conservative forces that are acting. So we shall also discuss on that, what exactly are non-conservative forces and conservative forces also, right? So this statement also culminates into a mathematical equation. That statement we've just mentioned right now. We are saying the Emec before in an isolated system is equal to the Emec after. Mind you, we are saying Emec is the mechanical energy to the Emec after. So that's a statement, a mathematical statement we are bringing in. Okay, let's try again to expand it further. We know, of course, Emec, we have already highlighted it as the sum of the potential energy and the kinetic energy. So we can also safely say EPI plus EKI is equal to what? EPF plus what? Plus EKF. That's what it means. So it means the sum of the potential energy before is equivalent to the sum of the mechanical energy after. The sum of the mechanical energy before is equal to the sum of the mechanical energy after. That's what this statement is saying. Okay, so let's try again to just make a small rearrangement. Okay, I'm just going to take EPI minus EPF, taking EPF the other side, and also EKF minus EKI. We're just rearranging the equation that we have created there. Right. Now this here, it is the change in kinetic energy. So we can safely say this is the same as delta EK, and we'll be correct to say that. But however, this is not a delta EP. So what can we do to make it delta P? We can factor out the negative, which means once we factor out the negative, we have EPF minus EPI. So therefore it means negative delta EP, which means it's also now the change in EP. It is equal to delta EK, right? So it means therefore the principle of conservation of mechanical energy can safely be mathematically be expressed as this. Will be correct again. So we can also say this is true in as much as this is also true. These two statements are true. That's the principle of conservation of mechanical energy, right? In order to apply this principle, we have to make sure that indeed the mechanical energy has been conserved. Now, how can we know, how to know if a mechanical energy has been conserved? How can we know that mechanical energy has been conserved in this case? How can we know that? Okay, so what we can simply do is we are checking, do we have any non-conservative forces that have acted? So let's first define what are conservative forces, and what are non-conservative forces. So let's start with conservative forces first. A conservative force, it is a force which when it does work, the work is independent of the path taken by the object. Right, let's try to understand clearly what this statement refers to. Okay, here is an object. It is lying on a horizontal surface. It's now understood, or it must be understood that there are forces obviously that are acting on these objects. Particularly, let's focus on the gravitational force weight. Gravitational force is acting downwards towards the Earth's center. Let's again take the same object and place it now on an inclined surface. Is the direction of the force, the gravitational force, going to change? No, it's still acting towards the Earth's what? The Earth's center. It's never going to change. So FG is still acting towards the Earth's center. Therefore, we can safely say if ever gravitational force is going to do work, the work is not path dependent. Rather, it is obviously because the gravitational force has a specific direction that it is following, it is acting towards the Earth's center. Hence, it's an example of a conservative force. Another example that we have is the magnetic force. It's an example of a conservative force. Another one, it's electrostatic force. It's an example of a conservative force. So these are the examples we have of conservative forces. Then we have non-conservative forces. Non-conservative forces. Now, which ones are these ones? Right. And by definition, again, what is a non-conservative force? So it's a question that often can be asked by the examiners. Define a non-conservative force. It's very important to take note of that. So a non-conservative force, it is a force which, when it does work, the work is dependent on the path taken by the object. So we are saying the force the work that is going to be done by the force is path dependent. Right. Let's go back to our horizontal surface where our object lies. Right. We have a force such as a kinetic frictional force, assuming that the object is moving to the right. There is kinetic frictional force that is trying to oppose the motion of the object. So it's acting obviously to the left. Let's now come on the surface, on the inclined surface. These are the surface. Now we notice that assuming the object is moving up the incline, we shall have, and also assuming the inclined surface is rough, there is kinetic frictional force. It's going to be acting down the incline. There is our kinetic frictional force, which means the kinetic frictional force is made, or is its path is made to be determined, or is actually being determined by the path taken by the object. Let's talk again of applied force, FA. Applied force having been applied on the object as it is moving maybe to the right. Let's go back to the object that is on the horizontal surface, right? Our applied force shall be acting to the right as it is moving the object to the right. Let's go to the inclined surface. Our applied force shall obviously act up the incline as the object is moving up the incline, which means these two forces I am giving as examples are obviously path dependent. They are the force of, or the work that they shall do obviously shall be path dependent. So whenever they do work, the work that they are going to do is going to be path dependent. That's what it means. So definitely we are saying these are non-conservative forces. So in the event that these non-conservative forces do not act or are not actually are not being found on an object, then it means mechanical energy is going to be conserved in such a situation. So examples of non-conservative forces, we have kinetic frictional force, we have applied force, we have tension, we have normal force, etc., among other forces. Those are examples now of non-conservative forces, right? So having explained that, having brought them out, let us now go back to our the principle of conservation of mechanical energy. We are saying in order to apply it, first make sure that mechanical energy has been conserved. So there is a common question that can be asked in the exam where they can ask you, has mechanical energy been conserved, or has the total mechanical energy in this system been conserved? How can you know? You simply check, do I see any non-conservative forces that are active? Which means if ever the work done by the non-conservative forces is zero, then definitely it means that mechanical energy has been what? Has been conserved. It would have been conserved if that situation is applicable. Okay, so that's our first energy principle. Let's go to the other energy principle. We also have the work energy theorem. We have the work energy theorem as our other energy principle, right? What does the work energy theorem state? What does it say? It simply states that the net work done on an object is equal to the object's change in kinetic energy. Remember, we said change in kinetic energy, or change in general, it is final minus initial. So change in kinetic energy, we have already witnessed that the change in kinetic energy is actually EKF minus EKI. So definitely we are saying what the work energy theorem is saying, it is saying that the net work done on an object is equal to the object's change in kinetic energy. Right? When we talk of work net, the net work, the total work that has been done, it is the sum of the individual work that is done by the forces acting on an object. So, assuming we have an object that is on an incline, let's give us an example. We have an object that is on an incline. It is being pushed up an incline by a certain applied force. And the surface is rough, assuming again that the surface, our inclined surface is rough. There are forces already that are acting on this object. So let's try to bring them out, which means W net is obviously going to be given by a work done by the applied force plus the work done by the kinetic frictional force. Remember, we are saying the surface is rough, plus the work done by the parallel gravitational force, plus the work done by the normal force, plus the work done by the perpendicular gravitational force. However, these two obviously will do work of 0 joules. Why? Because the angle between them, between the normal force and the displacement shall obviously be 90 degrees. So there will be 0 work that will be done by the normal force and the perpendicular gravitational force. So it means the W net is going to be given by the work, individual work done by these forces. So it means that if we sum up these forces, their net work is therefore going to be equal to the force, the change in kinetic energy, which can be given by half m Vf squared minus Vi squared. Definitely, where is that formula coming from, right? It's not saying much actually. Where it's coming from, we are simply saying that if we are saying delta Ek is equal to Ekf minus Eki, then it means also that half m Vf squared is equal to also plus minus half m Vi squared. Okay, so we can factor out the common factor half m, so that we end up having Vf squared minus Vi squared, of course. So that's where this is coming from, delta Ek. So we are saying we can equate this now to the work done, the individual work that has been done by all the forces that are acting on an object, all of them. This marks the work energy theorem. So far we have explained 2 energy principles. Then apart from that, there is another common statement again that we can also resort to, which is the work done by the non-conservative forces. Work done by the non-conservative forces is equal to the change in gravitational potential energy plus the change in kinetic energy. It marks again another energy principle. But this time around, we are only considering the work done by the non-conservative forces. So we can also resort to this principle, right? Apart from that, we can also safely again say net work done is therefore equal to work done by the conservative forces plus the work done by the non-conservative forces. These are the energy principles that we can resort to perform calculations, which means from here, we can now resort to calculations and see how our calculations are going to be done using the energy principles, just like that. So do subscribe to the channel and also like the videos, and also press the notification button in the event that we post something, so that you can also be always up to date. Okay.